This is section 2.2. We're going to continue our chapter on kind of logic and reasoning. And today we're going to do things called conditional statements. And this is going to be a lot of writing today. It's actually the basis for how we kind of start doing our arguments in geometry, which kind of come down to proofs, and that's our chapter 4 stuff. So I can write definitions as conditional statements. We're going to write some biconditionals today, and we're going to do some things called inverse, converse, and contrapositive. So first up, a conditional statement is just a logical argument with two parts. You have a hypothesis and a conclusion. And we have kind of talked about a hypothesis already. It's kind of our conjecture, kind of the guess thing that we're the guess statement that we're making. And then a conclusion is kind of what's the result of that. So the negation of a statement is just the opposite, of the original statement. Okay, so we've got a couple where we're going to start here. It says rewrite the conditional in if-then form. So we want to create an if-then statement out of our statement. So all birds have feathers. So what I tell kids is kind of identify the two main ideas. I got birds and I have feathers. So our if is going to be our birds and our then is going to be feathers. And we can't just say if birds then feathers. We kind of have to come up with a little bit more vocab to go around that, or a little bit more meat to the sentence. So we could say if an animal is a bird, then it has feathers. So I've got my if part. This is my my hypothesis, because if an animal is a bird, then it will have feathers. So those are my two parts, a bird and feathers. I kind of split them apart, added just a bit more verbiage to them to make the sentence make sense. And now it is in an if-then form. Two angles are supplementary if they are a linear pair. Well, right there's my if. So I can say if two angles are a linear pair, then they're supplementary. We're going to have to squeeze that in here. Then sup. Next one says when n equals 9, then n squared equals 81. You kind of get the then part right in there. You get that n squared equals 81. So if n equals 9, then n squared equals 81. So kind of look for those cues. If you see an if in a sentence or you see a then, they're kind of already telling you which part's the hypothesis, which part's the conclusion, and then you can just put it together in one sentence. So what is the negation for each of the statements? Remember, negation is just the opposite of the original. So if I say the ball is red, the opposite of that is the ball is not red. I will often have students say, well, the ball is yellow. And I'm like, well, is the opposite of red yellow? So make sure that you're just focused on being the opposite. So if I say it is raining today, then the opposite would be it is not raining today. Not we have hail today. You don't kind of change the context of the situation. If the ball is red, then the ball is not red. That is the negation. The cat is not black, then the negation would be the cat is black. So it's really just either adding in the word not or removing it. You are just flip-flopping when you're doing negation. Okay, now we're going to get into different ways to rearrange an if-then statement in order to provide kind of just these other statements that help us define and kind of construct our logical arguments. So we have something called the converse, the inverse, and the contrapositive. So we start off with our statement that I just say if P then Q. And I'm just doing that so it's generic. We could have if it's an animal, then it's a bird. If this, then that. So it's just kind of saying P is the first part, Q is the then part. So I could just say if it's raining, the grass is red. That could be my sentence. So this is our P, this is our Q. So if P, then Q. Whoops, then. So the converse of that statement flips them, and it does if Q, then P. So with our example, it would be if the grass is wet, then it's raining. Not necessarily a true statement, because I could just have the sprinklers on. But converse just flips them around, flips the hypothesis and the conclusion. Inverse leaves them the way they are, but it negates it. So if not P, then not Q. So using our example, it would be if it's not raining, then the grass is not wet. Of course, that might not be true. I could have the sprinklers on, so it's not really raining, but the grass is still wet. Contrapositive, you flip them and negate them. So if not Q, then not P. In our example, it would be if the grass is not wet, then it is not raining. And I kind of match up the two C's, contrapositive and converse, because they go together. The Q's come first and the P's come second. And one of them is the plain if then, and the other one has the nots. And then this inverse has an I, and so does the if then. So that's kind of how I remember who goes with who. And P and Q, these ones stay P and Q, they just happen to have knots in front of them. So it's kind of how it's a little trick I use to keep them straight in my head. Now we're going to do a couple of examples. So first we're going to write the if then, and then we're going to write the converse, the inverse, and the contrapositive. So first I've got guitar players are musicians. So just like up above with birds and feathers, we kind of want to identify our two things. So we've got guitar players and we've got musicians. And now we need to separate them as an if then, and then just put a few more words around it so it makes a sentence that actually makes sense. So how about if you play guitar, then you are a musician. So the converse would flip those. If you are a musician, then you play guitar. And we know that's false. Our other job here was to do true or false. We know that's false. I could play the drums. And that is my counterexample. We talked about that in the previous lesson. You just have to provide me one way that your statement is false. Inverse, I'm going to go back to the original, and I'm just going to put knots in it. So if you don't play guitar, then you are not a musician. So it's just the addition of the knots. Whoops, that's not how you spell musician. C-I-A-N. And we know that's false. Same example. You could play the drums. You don't have to play guitar to be a musician. Last up is contrapositive, and remember you flip them both. So you flip P and Q and you add knots. So converse and contrapositive go together. Same sentence, you're just going to put knots in there. If you are not a musician, then you do not play guitar. I would say that's probably true. If you don't consider yourself a musician, you probably don't play any instruments. Well, then you wouldn't play guitar either. So I would kind of consider that to be a true statement. We're going to do another one. We're going to make the if then, and then we're going to do the inverse, converse, and contrapositive. So this one I've got, if you are not in 10th grade, then you aren't a sophomore. So the converse of that, converse, remember, is going to switch them. So if you aren't a sophomore, then you aren't in 10th grade. And I would say that's true. You need to be a sophomore to be in 10th grade. The inverse is going to keep them the way it was. So you're going to use your same statement, only you're going to negate it. So we have knots this time, so we're going to take them out. If you are in 10th grade, then you are a sophomore. I would also say that is true. By definition, 10th graders are sophomores. Contrapositive. You flip them and you negate them. So for us, that's taking out the negative. So contrapositive, we're just going to take out the negative. So if you are a sophomore, then you are in 10th grade. And I would say again that that's true. If you're a sophomore, then you are in 10th grade. And why do we do all this? Because later on we're going to be starting to make our arguments for geometric proofs, and we actually talk about converse. We're going to talk about converse here in a second when we make our biconditionals. But oftentimes in math, we want to look at the definition from both directions. So if the second part is true, like if we flip it to if we flip it to contrapositive, and you are flipping both ends and they're both true, you can come up with other statements you can say. So it's kind of an interesting mathematical oddity to be able to construct all these logical arguments. So a biconditional, that's our last word for today. A biconditional is a statement that is true as an if, is true as an if then. If then. So like your original statement is true, and true as a converse. So using this example up here, so if you're not in 10th grade, then you're not a sophomore, and if you aren't a sophomore, you aren't in 10th grade. Both of those statements are true, forwards and backwards, and so that makes that a biconditional statement. We're gonna do all birds or feathers, sorry. And one thing about biconditional is it contains right in the middle, it contains if and only if. You can abbreviate that as IFF if you'd like, if writing that out is just too much for you. So on the first page we had, I gotta find it, if an animal is a bird, then it has feathers. So the converse of that would be, if an animal has feathers, then it is a bird. So both of those statements being true, we're gonna write it as a biconditional. And again, your two ideas are birds and feathers. And in the middle of the statement, you're going to write if and only if. So this happens, if and only if that happens. So to use this one, it would be if you are not in 10th grade, if and only if you aren't a sophomore. Or it could be conversed around. You are not a sophomore if and only if you are not in 10th grade. So you're just saying that this definition is true both directions. Both if-thens, the original and the converse, are both true. An animal is a bird if and only if it has feathers. So that is how we took that statement and we turned it into a biconditional. And it has to have that if and only if part for it to be a biconditional, so make sure you don't forget that. And if you notice, there's no if at the beginning and there's no then at the end. The if and only if kind of takes care of both of those parts. So that is another day of logical arguments, a lot more writing than there is actual math. But we're going to set ourselves up to be able to do proofs later on. So this is our good base.